It's going to have a talk on extreme events and the multifractal butterfly effect.
So, good afternoon. I'd like to thank the organizers, especially Valerio, for giving me a chance to come back to my alma mater 40 years later. Well before the Isaac Newton Institute existed, of course. Anyway, it's been a pleasure. And I'm afraid, I guess I should apologize in advance to Michael, because there will be some multifractals in there. And he said, of course, you're not talking again about multifractals, Shaun.
Surprise.
So, okay, well, in fact, it's true that a certain amount of the mathematics is not so new, but perhaps not so well known in this community. But I'll assure you that I'm mostly going to be talking about some of the applications, and those are, in fact, quite recent, so at least the ones I'm talking about. So the other thing is that this is a bit of an unabashed advertisement for my book that just came out with Daniel Schertzer, and in fact a lot of this work was done in collaboration with him. Okay, well, everybody seems to be showing pictures of people that who are predecessors. This is a slightly different collection, perhaps, although this picture actually has been shown many times in Richardson. But we're all used to the idea that science is a kind of a hierarchy of interlocking theories, and there are fundamental theories, such as, say, statistical mechanics, and you could even go more fundamental into quantum mechanics if you like. But these theories are often not very useful in many applications. So, for example, in the earth sciences, we're mostly interested in using continuum mechanics and thermodynamics. So this is, many of you here, I don't want to offend, of course, use statistical mechanics, but clearly, if one can use continuum mechanics and thermodynamics, then it's much more convenient. And it was the belief, though, of these pioneers of turbulence, classical turbulence theory, that there were indeed higher level laws still which applied to fully developed turbulence, high Reynolds number limit, essentially. And these laws were supposed to come out when you had, this is the sort of spaghetti plate view of high Reynolds number hydrodynamic turbulence. So we're looking at vortex tubes. The idea is, you have all these kind of spaghetti vortex tubes interacting with each other. And one expects to get laws that, like Richardson law, Kolmogorov law, Corson, Abukov law, Bolgiano-Abukov law, and others, and they're all of this kind of a form where, say, you have the fluctuation, in this case for the Kolmogorov law, for the velocity component, the difference in the velocity component across a vector delta r goes as some turbulent flux. Well, in fact, this is the energy flux to the 1/3 if you have the Kolmogorov law, then times the separation distance to some power, and for the Kolmogorov law, okay, these are the values. But Kolmogorov himself thought that the assumptions necessary for this law to hold in the atmosphere were so stringent that it would not hold over more than something of the order of 100 meters. And in particular, you have an assumption of isotropy, because this is just a vector norm, so it doesn't depend on the direction of delta r, whereas we know, of course, gravity is of course important, fundamentally important in the vertical. There are other sources of anisotropy, Coriolis force, etc. And the other thing is that Kolmogorov derived his law under strong assumptions of essentially smoothness, that the energy flux was more or less the same everywhere. In other words, there was no intermittency in the problem. So what I'm going to discuss today are the fact that one can take these classical laws and generalize them so that actually they're valid much more generally, in fact, up to the size of the planet, as you will see. But to do that, okay, we may need to generalize the notion of fluctuations. You can use, of course, wavelets to do that. We could, so we get rid of the idea of a smooth and more or less constant energy flux to take into account, in fact, a multifractal, a highly intermittent flux from a cascade. And then the notion of scale itself has to be generalized to take into account anisotropy. So I won't discuss that aspect so much, but okay, so one gets laws something like that. I'm going to just concentrate on the turbulent fluxes. So this is then, your sort of familiar idea of a cascade, sort of a caricature. You have a large structure called the parent, and for some reason the smaller ones are called daughters and not sons, but anyway, that's what they're called. And if you have a homogeneous cascade, then of course you just redistribute this energy flux from large scales to small scales. So the physical picture is, usual thing, you kind of have some kind of quasi-steady stirring at the large scales, and then you have this cascade of this energy flux that goes down to the small scales where eventually it's dissipated by viscosity. So this is your homogeneous cascade, a simple way of taking into account intermittency, but it's very drastic, is from time to time to kill off one of these eddies. So you have dead or alive, and you end up with a fractal distribution of active areas. But of course, turbulence is not just dead or alive, but you have all these intermediate levels of activity. So in fact, you can just change that intermittent model a little bit. Let's say we have this square region here where we're trying to model the intermittency, the energy flux density. We can divide it up by half in each direction and flip a coin. Sometimes we boost the energy flux, sometimes we decrease it by some factor, and then we can repeat, we break it up, and you keep on multiplying. And if and you can make a constraint that on average the energy flux density, the integral of the energy flux density underneath this curve here is conserved. So from each step to each step, on average, you have conservation. Turns out that's a key point. That's called canonical conservation. Unfortunately, most of the literature, at least the physics literature, is concentrated on a much more stringent relationship between the large scales and the small scale called microcanonical, in which case all kinds of things that I will tell you no longer hold. And specifically, the extremes are badly truncated. And since we're talking about extremes, I want to concentrate on these more general cascades. But what you can see is that you go down here and you get, because you've got this conservation of the flux on average, if some of the regions have repeated many boosts, so they get spikes, then there's going to be a compensating, most of them will end up being quite low. And you can see this is in fact a multifractal in the limit. If you just took a cut through here and you look at the set of points that exceeded some threshold, you would get a fractal set, and the dimension of that fractal set would decrease. If I went to a higher level, I'd have a different fractal set with a lower fractal dimension, etc. So that's your multifractal. And the key thing we need to know for the rest of the talk is that the generic statistics of these models, if you look at the ensemble average of the qth power of the cascade after being developed over a range of scale lambda, here it's 128, 2 to the 7. It goes as the scale ratio to some exponent, and that's a convex function. And so, of course, this has all the information about the statistics of the process, this k of q. Okay, well, I don't want to dwell on this too much, but of course, that was kind of a toy model with those straight lines and factors of 2. And actually, we really have a continuum of scales. So what you have to do is to make a continuous in scale cascade process. To do that, essentially, since a multiplicative process, you're going to model it as the exponentiation of an additive process. So you have a generator, the gamma, which you exponentiate to get your multifractal. And the generator is basically can be obtained by an IID Levy noise, and then convolved with a singularity of a certain order. In fact, basically, in Fourier space, it's simply a power law filter. The exponent has to be carefully chosen so that you get, in fact, these statistics down here. But basically, then, a power law filter, it's a fractional integration. It's a scaling operation. The statistics, when you do that, are indeed like this. And the exponent, though, if you take this particular recipe, gives you it's a 2-parameter exponent. There's the alpha from the Levy index of this generator, and then there's a C1 that tells you about the intensity, in fact, about the intermittency of the mean of the process. Okay, and you can imagine that if you start from some slightly different cascade, that you could that there would be some kind of multiplicative central limit theorem that would give you this type of behavior. And so it's a kind of a stable, attractive, stable behavior, and that's why it's quite interesting. Now, the only thing is that this is actually not valid past some critical level. This is valid for the small moments, but not for the large. For the large order moments, you get generally this type of hyperbolic power law tail. That's what I want to come back to. That was first pointed out by Mandelbrot, in fact, quite a long time ago. But you can see what's going on here. Coming back. So this is what I discussed, building up the cascade step by step by step. You get to some point here. That's all very well. There's no extreme, well, the tails may be, say, log normal or log Levy, but they're not more extreme than that. All the moments will converge. But if one then averages out, so one averages, so you can get something with the same resolution, but you've just averaged out this small scale variability, well, one doesn't actually average it all out. One can compare this thing here, which you develop after a certain range of scales, you can see, and this one here, where you've gone much further and then averaged to the same resolution. You can see many of the structures the same, but sometimes one gets much stronger fluctuations, okay? And that's this divergence of moments. Whoops, what happened there? Okay. All right. So, okay. So I'm going to just try and finish this brief exposition of things. So, okay. So you've got this part corresponding to turbulent flux. The observable, let's say the velocity component or the temperature or some turbulent variable, then is going to be equal to the cascading flux, essentially fractional integral convolved with singularity. Fourier space is just this multiplication. And then you get, for example, the qth order structure function. So the fluctuations of the field just end up going as the distance separation to some psi of q. Psi of q then has a linear part due to this last fractional integration, and then it has this convex part due to the scale dependence of the flux. Okay, so we're not going to be talking about the observables, but actually the field. So how do we get the fluxes from the data? Because I want to show you that indeed you've got huge ranges of scales where this works very well in the atmosphere. So one starts with this sort of generic turbulent law, and then one can just take ensemble averages and then divide this is the level of fluctuation by the ensemble averages, and one gets the flux at some scale. If you do this at a very small scale of your data, this gives you your flux field at some small resolution, and then you can just degrade it to some lower resolution by, say, averaging. And so when one does this, let's say this is for rain rates, you can look at the rainfall from satellite, from reanalysis, from gauges, 20,000 kilometers to 100 kilometers here. One gets these nice straight lines, and the point is that, see, you're expecting the moment's qth moment to go as lambda to the k of q. So when lambda is 1, then there's no variability. 1 to any power is 1, of course. So and if you take log of m against log of lambda, one should get a straight line with slope k. And you can see that they do indeed follow this rather well, as long as the outer scale is actually somewhere a little bit larger than 20,000 kilometers. And so that's the effective outer scale. Clearly, what all that means is that at 20,000 kilometers, there's still some variability because the rain field is coupled with other fields. So it's the variability at any scale in this range from 100 to, say, 20,000 is almost exactly the variability that you would have had if you'd had a cascade starting at actually about 30,000 kilometers. Okay, and you can get very similar results from other types of data. This is, say, east-west wind, north-south wind, temperature, humidity. So it's always a little bit variable at 20,000 kilometers. You can see there's a bit of deviation here. This would correspond to about 10,000 kilometers here where you're getting this kind of deviation. But over most of the range, it's excellent. Okay, this is more reanalyses, just different fields. This is a different kind of this is the ECMWF reanalysis. The other one was the 20th century reanalysis. You can look at weather models. You can look at different forecast horizons and whatnot, but they're all this very nice kind of behavior. You can look at the forcing of the atmosphere, visible. It's from satellite data. So this is essentially the energy input. Very nice cascades. Again, the outer scale, something near 20,000. Or you can look at the the microwave thermal IR, which is basically your energy emission. You can look at aircraft data. This aircraft data stopped at about 1,000 kilometers, but you get, estimates for temperature, humidity, whatever, very close to nice cascades with, again, nearly 20,000 kilometers. If one looks at the vertical, of course, I won't have time to discuss this very much, but basically you have different exponents in the vertical and horizontal. So this is what the vertical section of your sort of toy model cascade would look like. You break up, start off with something flattened in the horizontal, and you break it up differently in the horizontal and vertical. You can have homogeneous, fractal, and then, of course, multifractal. Okay, so here you can look at the same. This is a vertical section of LiDAR data, essentially from aerosols. You can get this is the horizontal. So again, 20,000 kilometer outer scale, but in the vertical, it's more like 20 kilometer outer scale. And you have different exponents. And you can look directly at the vertical with things called dropsons. Okay, so I'm just trying to convince you that you can get, the cascades work very well up to essentially the largest scales. So therefore, you should take seriously the consequences of the cascades for the extremes. And I've already given you the idea that it will, in general, give you these power law tails. And the reason is because of this thing called dressing, which is you have the Baire cascade. This is sort of renormalization jargon, is just the cascade, say, from scale 1 to a scale lambda times smaller. You can make a cascade from scale 1 to a scale capital lambda times smaller by taking this other partially built cascade and shrinking it appropriately and then multiplying that times that. There's this factorization. That's just the nature of the cascade. And then what one does is one is just going to be integrating out the last range of scales. So it's like going up that right-hand side of the picture I showed you before. I then integrate out these fluctuations that I've put in. And so then I get the statistics are a Baire cascade multiplied by a thing called a hidden cascade, which is your cascade that essentially has been averaged out. But you don't average everything out. There's still variability. So in the limit, you get this at a certain scale range lambda, you get this dressed flux. It's the Baire flux here times this hidden factor. And so that's this relationship here. And the key point is that this thing you get by essentially is equivalent to a completed cascade that's integrated out. It has the property that the qth order moments are of order 1 for q less than some critical value qd, and they're infinite if you exceed that. And qd, in fact, just satisfies this relation here. K of q then is this thing that tells you about how the moments scale. So there's an equation for that. And so what you find is then, in general, okay, the moments, these correspond to, of course, things that you measure. Because if the cascade goes down to a millimeter and then you average over a kilometer, you've got something closely approximating this addressed thing here. Then you get this thing here, this transition from a finite value to an infinite moment. And that could be put in the framework of multifractal phase transitions. And okay, so I won't go into it. Of course, the divergence of statistical moments corresponds to this type of probability tail. And of course, because of the long-range statistical dependencies in the cascades, this is actually outside the framework of extreme value theory, even though, of course, this could be part of the Fréchet type of extreme. But there are strong long-range correlations. Just to mention, this is, you could think of this as being connected to self-organized criticality. So there's this idea introduced by Back and Tang in 1987. Was this sort of sandpile model where you had, the idea was that these kind of typical behavior of the system is actually the result of extreme events like avalanches, essentially. But this is what I'm calling classical self-organized criticality. The thing is that was limited to essentially a zero flux limit. So you had to, in the sandpile version of this, you had to add one sand grain at a time and wait for the avalanches to stop. Add another one, wait for the avalanches to stop. So not really very appropriate for, say, a turbulent system. So this non-classical multifractal sock then assumes a more or less quasi-constant flux from large scales to small scales. Okay, so it's more appropriate. Just to show you that you can get this working out in laboratory turbulence, So if we have this energy flux goes as a power law, then in the dissipation range, the energy flux is related to the viscosity. So one gets this type of relationship. So one measures, say, the velocity fluctuations and looks at the probability distribution of velocities, and one should get then this relationship between the exponents, the velocity and the energy flux. So there's a half because of the exponent 2 here. In the inertial range, though, one gets this type of relationship, and then you get a 1/3 power. And in fact, this works out extremely well. This is results from one of my ex-students, Radulescu, some years ago. We used laboratory turbulent data, and he looked at, first of all, the inertial range, and then the dissipation range, and well, he got these type of exponents for the velocity, 7.7, 5.4, and you can see that they give very close, almost the same estimates for the exponent for the dissipation. So one can explain then laboratory turbulence this way. This is just showing the compensated. So that's, it's this problem we discussed at the end of the last, or somewhere earlier in the last session, that you've got these more or less straight lines. Well, you don't know exactly where they start. You don't know what the exponent is. So the best you can do is kind of try and you can put a straight line. You could compensate and see how flat. Okay. In the atmosphere, going from the atmosphere to the lab to the atmosphere, still with wind, this goes back some time, but you get actually about 5 for the exponent, but this is in the vertical direction. This is aircraft data in the horizontal, and you could also do this in time. You just sit at a point, and so there's quite a few results going back now, nearly 30 years. I just did a survey of all kinds of geophysical evidence for divergence of moments. You can see there's a huge range there's loads and loads of things that have been done. Many of the exponents between about 3 and 5. This is just supposed to give you an idea of some of the stuff that's been done, and I'm sorry if I've missed out some stuff. This is things to do. These are to do with rain and hydrology. One comment. Let me see. This thing is not advancing. I think I just have to be patient here. Well, it seems to have trouble loading the next. I think it's loading the next slide. There we go. Okay. Whoops. All right. Right. So, okay, this is just for a comment about rain. If you look at, this is actually gauges, hourly fluctuations in gauges, but you have nearly 10 to the 8 data, so you go down quite low in probability. Seems to be not too bad for third order divergence. But when you look at reanalyses, you don't get the tails. The thing is, that's what you would expect, because if you have a cascade process, then the reason you have these tails, these extreme tails, is because of the large range of scales. The variability builds up scale after scale. So if you have only a small range of scales, you will not expect to get the tails accurately. So this then, okay, another application is to do with abrupt events, extreme changes. Here we have, I think this was more or less shown 2 days ago, in fact, this ice core data from Greenland. I've got backwards. In other words, this is the present and this is the past. But you can see this is our more or less warm period now, but the ice age has got all of this, these huge fluctuations, and some of these spikes where you can sort of go in and out of an ice age in as little as 10 years, or these Dansgaard-Oscar events. But one might expect them just on the basis, if you look at the probability distributions, that you have some evidence for power law tails. And in any case, the extremes are very, very far from being a Gaussian. If this was a Gaussian, this point would have a probability of, very 10 to the minus 47 or something. Just to indicate, you can analyze the data both in depth and then in time. In time, you need to interpolate, and this can introduce some problems, as you can imagine. So, okay, but I don't have time to go into that further, but the idea is that, okay, you can get these abrupt events coming out naturally without some other explanation. There's just a continuum of fluctuations, and some of them are big, and that's what you expect. All right. Just a last little example, which is quite recent, but maybe interesting to people here. One can try and do what I call a GCM-free quantification of anthropogenic warming. I think this is badly needed because lots of people don't believe the models. And it's nice to be able to analyze things without them if one can. What the idea is that if one has a strong enough anthropogenic warming in, say, the last 125 years or so, industrial epoch, then one can consider that the natural fluctuations, sorry about that. The natural fluctuations are a kind of a perturbation to an anthropogenic part. Now, the new thing here is what I'm doing is I'm assuming that all of the anthropogenic effects are taken into account, at least linearly, by using the CO2 forcing as a surrogate. That means that I'm using the fact that, say, the concentration of methane and other greenhouse gases are highly, their forcing is highly proportional to the CO2 forcing. Why? Because economic activity is driving the increase of all of this. The same is true for aerosols, which generally are going to be having a more cooling effect and which are currently hotly debated, but they're still highly correlated with economic activity. So whatever the actual effects of those things are, I'm using then the CO2 forcing as a surrogate, and that is basically the log of the concentration here. Okay, so what one can do is then one can plot the global temperature since 1880 as then a function of this forcing surrogate here. It's the log of the CO2 compared to the pre-industrial level, and one gets, as one can see, really a rather nice linear relationship, rather high correlation coefficient. Now, this was actually the original data that I analyzed. It was only available in 2004, and then because of all this talk about the so-called pause in the warming, I decided to put on some more recent data, and you can see, so this is what they call the pause, the fact that recently the temperature has not been increasing very much, but actually, if you fit the entire data, including the last couple of years, you get the red line, and if you don't include them, you get the black line, and you can see that it doesn't change the fit by very much. So in other words, the pause is actually more or less expected. Also, with this method, there's some other stuff you can go into, but basically one can use the slopes of these lines to predict this climate sensitivity, and one gets, with 95% confidence, one gets a value between about 2 and 4.25, whereas, as was mentioned earlier, the IPCC5, hot off the press, is about 1.5 to 4.5 degrees. 2 minutes, I'm nearly done. Okay, that's with high confidence. Okay, so you get, in fact, more or less exactly the same result, but with a narrower range there, and you don't need GCMs, and okay. Oh, and this, okay, so why can I have some confidence in this? Well, one can analyze the residues. So this is what it looks like if I go back to time against temperature. So I use this as the relation I just derived by the linear regression of the forcing. So the residues are these things here, which I'm interpreting as the natural variability. One can take multi-proxies to look at annual temperatures over a 125-year period in the pre-industrial. So you've got 125 years here, 1500 to 1624, 125 years, 125 years, that's what it looks like. And then, of course, this is the last, 125 years, 1880 to 2004, so you can see it's going way up. But when I remove the anthropogenic part, one gets this residue here. And in fact, the statistics of this are almost the same as the statistics of these other curves. You can see that this then, the multi-proxies, this is the average variability of the fluctuation, RMS variability of fluctuation as a function of time scale. This is the RMS variation of that, and this is the residuals. So the residuals are almost the same, have almost the same statistics over this range of scales as do the pre-industrial statistics. So it's kind of a verification, and this is my next to last slide here. Okay, so how can I do this to try and test, because this hasn't actually been done, to try and do a proper statistical test. What's the probability that the observed warming was essentially just a natural fluctuation? Well, one can look at the probability distributions pre-industrial using these multi-proxy data. You can look at the fluctuations over 1 year, 2 years, etc. I've shifted these a little bit it's shifted by delta t, just so you can see them more clearly. But the actual data are these red curves for the probability distributions, the probability of exceeding a threshold, so log. So a straight line is a power law. And one can see that I can bracket the tails between roughly these two green lines corresponding to actually QD is 6 for the exponent and QD is 4. So all I'm going to assume is that the reality is somewhere between there, although in fact if you do some statistics you find that the value should be closer to about 5, but let's just say it's between 4 and 6. Dashed lines would be Gaussian. And so when you do that, and then you have to use a hypothesis about how much warming there has been. Various estimates give you something like 0.85 degrees warming since pre-industrial. That corresponds to nearly, between 4 and 5 standard deviations, in fact. And all right, depending on what exponents you take and exactly how much warming you assume, but basically all the estimates give you pretty much, probability of the natural fluctuations being something like 0.1%, but always less than 1%. One can see that if one had a Gaussian tail instead, then it would be something like 10 to the minus 6, 10 to the minus 7. So one's taken into account these long-range statistical fluctuations. So you have long-range dependency taken into account. I went through that very quickly, but the statistics are not just Gaussian or anything, not just exponential decorrelations, power law decorrelations, but they also have power law tails. So I stop there. Right, I don't think I have to repeat any of these conclusions, but okay, stop there.
A couple of minutes for questions. Who wants to break? I think we're getting terribly tired already, I think. One thing that surprised me when you do this fitting, of course, why do you really sort of insist on having these exact linear approximations in the tails? Because of course you could have this slight curvature if you do slightly more general GPD fitting. Because you can sort of also, I mean, some of the pictures I saw before, you were really getting these tangential lines perfectly. Well, there.
Okay, this one is maybe
really smooth. You could really have your models, your extreme value models, would typically curve it within the tails. If it's a question of getting the, because of course you really insist on this exact tail behavior power.
Well, all right. No, I admit. I mean, all this theory could admit log corrections of the kind that you were talking about, and
the GBD fit would really sort of curve in your tails also. And
I mean, okay. I mean,
that'll give you better predictions of your quanta.
All right. I mean, that's maybe quite a good idea. Yeah. All right.
Yeah.
I mean, obviously, we're at some level we're arguing for the plausibility because here there are obvious difficulties in interpreting the data because on the one hand, basically, you have this. So you do it in terms of depth, you do it in terms of time, and there's a difficulty.
No, I just adjusted. Okay. Any other question? Yes, please.
Related to the intermittency, I'd like to know your opinion about the following fact, which was very well known in time. For a Langevin type equation, if you solve it in complex time plane, the intermittent events appear exactly where you have singularities of the solution in the complex time place. Now that was finally evolved to integrability and other, but the idea remains. And as far as I know, if you solve this, you obtain so many singularities that they may be on a multifractal. You know something about that? I mean,
no.
The theory, I think, has not evolved exactly in that direction. It would be interesting. It's Frisch and Moff is at the origin of this idea. But as I said, it evolved into the direction of Penlevet properties and integrability, etc. So, unfortunately, it was not fully exploited, in my opinion, in what is relevant for the turbulence.
So I don't know the.
Okay, so I think we should move on to the next paper. Thank you very much. Very informative talk. Good contribution. Thank you.